Valeria Pettorino, using Python in cosmology. Thank you.
Okay, can you hear me? Yes. Great. So good morning, ladies and gentlemen, and let me first thank a lot the organizer for inviting me. It's really an honor, pleasure to be here. And I'm Valeria Pettorino. I work at the CEA, the Commissariat pour l'Énergie Atomique in Paris, in the Cosmostat laboratory. And I will be bringing you to space and illustrate what is it, the dark universe, and how we use Python in cosmology. So let me first tell you a little bit about myself. I'm a physicist. I work in astrophysics and in cosmology, so in the study of the universe, of the evolution of the universe, and all the forms of energies which are in the universe. And in particular, I am part of two satellite experiments, two collaborations. One is Planck, that was launched by ESA and NASA in 2009, and it's finished, let's say, collecting the data. We had the main release last year, and we will have a last release of the data at the end of this year. And the next challenge is Euclid, the next satellite that is going to be launched by ESA and NASA in 2020. I've also worked in communication and in data science, actually separately for a healthcare IoT project with the S2DS, which is a science to data science program that is meant to bridge scientists also to work on data science. Okay, so at which distances are we looking at? What is cosmology? It's very, very, very large distances. So if this is dimensions in meters, and the human beings are typically of the meter, we go farther up to beyond Earth, which is about 10 to the 6th meters, beyond the sun, in astrophysics, and in cosmology. So 10 to the 26th meter, the whole universe. And just to give you an idea, we are on Earth. Earth, for what I do, is basically completely negligible. We go behind, far, far away to our solar system with all the planets. And farther away, the whole solar system is somewhere here at the edge of our Milky Way. That's our galaxy. And farther away, we just move farther away from our galaxy. Every single point here is a galaxy like the Milky Way, really observed. That's a picture, really of real observed objects. And if you imagine to go even farther away, and you can, hopefully this works. So imagine to go farther and farther and farther at very large scales. How do you expect all the galaxies to be in space? They're not homogeneously distributed, they're not with the same density everywhere, but they actually form something that we will see in a moment. So these are real galaxies which have been observed by the Sloan Digital Sky Survey. It's a telescope actually from Earth. And each point in this video is a galaxy which has actually been observed. And as you go farther and farther away, you see that there is a web, which is called the cosmic web, where all these galaxies are placed. So we know a lot about the universe. We have actually seen that. And okay, you see the black cone just because the telescope didn't observe in that direction, but all the rest has actually been seen. And what we know also is that the universe started 13 billion years ago and then expanded. And as you see, the expansion is mainly first happening in a decelerated way, so because of gravity that tries to keep everything together. And then at some point, 5 billion years ago, suddenly it starts to accelerate, so to increase velocity, as if there was some other source of energy that pushes, that contrasts gravity. And this is what is being named dark energy. So that was actually the observation of the accelerated expansion was due first to these three guys who got the Nobel Prize in Physics in 2011 for experiments on supernovae, so on the end of the stars. And then after that, there have been many, many experiments, independent experiments from different collaborations, from ground and from space, who have actually confirmed this incredible, surprising picture, in which there's not just gravity pulling things together, but there's something else that accelerates the expansion of the universe. So that's our, say, energy budget in the universe. And the surprising thing is that us, and basically all stars, so all atoms, all ordinary matter, is just about 4 or 5% of the total energy budget. All the rest is dark. Dark, it's either in the form of dark matter, so a form of matter that it's still feeling gravitational attraction, but it's dark in the sense that it doesn't emit visible light. And the rest is even more mysterious. It's called dark energy, and it's about 70% of the total energy budget. So in practice, we are just using less than 5% of our energy. And we have no clue, more or less, of what's the other 95%. And that's really something that only came up in 1998 for the first time, where there were the first experiments on supernova. And since then, in the last basically 10, 15 years, the major challenge in cosmology and astrophysics is mainly to understand what is this dark universe. And this is a big data challenge. And it's really the target of the next generation of experiments like Euclid, which are going to use different probes to, and combine them to scan the sky in different slices in the history, in the evolution of the universe, because the farther we look in space and the more we are looking in the past. So we can slice the evolution of the universe in different epochs and really observe that, observe galaxies, observe how the light that comes from the past reaches us, how it's bent by the matter and energy which is in space. And from that, we can understand, hopefully, what the dark universe is. So that's a big challenge from many points of view. Is a challenge for technology to actually build these detectors, especially if they're in space. It's a challenge for the signal processing. So most of the activity in the Cosmostat lab where I am in is really on the signal processing problem, because we don't just see galaxies with a nice, clear picture. Of course, we see them like more, let's say, like that. So on the right side of the image, with lots of noise, lots of foregrounds, lots of other sources that you have to delete. Pixelized images from which, using very advanced statistical techniques, and also machine learning, actually, we try to extract the actual shape of the galaxy. And from that, after this is done, there is a whole new challenge in which I'm mainly working on, which is the interpretation. So how you actually get from the shape of the galaxies to test really physics, gravity, and understand what this dark universe is. So this is not anymore the job of a single astronomer. Now in cosmology, cosmology mainly works with very large collaborations. So Planck, the Planck satellite, the first one in which I've been working on, includes about 500 people from all over the world, 100 institutes in Europe, US, and Canada. And the other one, the next one, the Euclid, which is going to be, again, sent in 2020, it's now 1,400 people from 120 laboratories from different countries, including actually Italy has a very important role in it, and US, and recently also Canada. Okay, so let me tell you a little bit about what we actually did for the analysis I coordinated for the Planck satellite. This was launched in 2009, and we collected terabytes of data. So the satellite was launched to 1.5 million kilometers from Earth, on the other side with respect to the Sun, and it was rotating, scanning the entire sky twice per year. So that's a spacecraft. And it was kept at a very, very low temperature because its objective was to detect the cosmic microwave background. So the light that was emitted just after the Big Bang in all directions. So it was it managed to have a full sky map of this, basically. You might have seen this. It was in several newspapers at some point. So that's the light that was emitted 380,000 years after the Big Bang, so basically 13 billion years ago. And all these dots and different colors represent differences in temperature of the light that, again, passed through everything in the universe from all directions and reached us. So this is something equivalent to what you might have for example, Earth temperature. So it's just the map of the sky, and so that would be, let's say, the temperature on Earth going from, I don't know, minus 60 to 40 degrees. And that's the equivalent map of the temperature in the sky, in the microwave, of this primordial radiation. So it's a picture of the baby universe, as sometimes it's called. And the amazing thing is that here, differences in temperature are really tiny, tiny differences, if you see the scale. It's really 1 part over 10 to the 5th. And we are able to detect these very, very, very tiny differences in temperature, which is also challenging because that's the reason why the detector has to be at very, very cold temperature, 0.1 Kelvin. It's the coolest place in the sky for a while. So to be able to see this radiation, cosmic microwave background, so a radiation in the microwave, which came from the primordial universe, you need to first, let's say, remove all other sources, so all other stars and radio emission from our own galaxy, which is just a sort of background. We're going to get rid of it. And all the dust that is in our galaxy, in the Milky Way. You remove everything until you actually see what comes from really far, far away. So that was the main release from last year, so you might have seen that picture. And to get to that, is a long, long process. Because at the beginning, when we actually get the data, we just get time-ordered data like this. That's just 3 minutes of raw data in different frequencies. The data arrives to the data processing centers that for the 2 satellites, for Planck and Euclid, they are in Italy, mainly in Trieste. It's one of the largest data processing centers, and in Paris or Toulouse for these 2 experiments. There are several classes which are used also in Geneva and in the US, and also some in Canada. And that's really, at the moment, it's terabytes. In the next future, for radio telescopes, it will be terabytes per minute that we will get and we will need to analyze. So from the satellite, in between there is also, there's Germany also, where there is the Darmstadt Center for ESA, for the European Space Agency. From the data processing centers, we extract, with a very complicated, again, signal processing, we extract the map that I've shown you. And then since this is in the sky, typically this is projected into spherical harmonics. So we extract part of the signal. And all this involves lots of programming, of course, and lots of different codes that are used by different groups and also historically, let's say, have been used by different groups in time. So not only Python, I must say, there's lots also in C, in C++, and also Fortran, actually. Okay, from the map, you can extract into spherical harmonics the power spectrum. So you extract, that's basically temperature fluctuations, very different, very small, these tiny, tiny differences in temperatures that we have seen in the whole sky map as a function of the multiple, so as a function of the scale that you're looking at. So that's smaller angular scales, and that's large angular scales when you compare differences in temperature at large or small angular scales. And then once you have the data in this form, so you have already reduced a lot from the originally terabytes, you try to fit them with some model that contains lots of information about the evolution and the content of the universe. And quite surprisingly, actually, quite amazingly, the standard model now in cosmology has just 6 numbers mainly, and it fits the data very, very well. And these 6 numbers only work if you add dark energy and dark matter. If you add only atoms, there's no way you can fit that. Actually, maybe if I have time at some point, I can show you. There's, So that's the cosmic pi that we have seen that basically corresponds to that line that fits the data very well, that contains this, more or less, this percentage of dark matter and dark energy. If you go to this link, I don't know if you can see that, or I can give it to you afterwards, you can actually play on the NASA website and try to fit the curve with like changing the amount of atoms, changing the amount of dark energy, changing the amount of dark matter, and you'll see that that's the only way in practice in which you can fit the data. Okay, there's a collection of tools which is used in cosmology and which is available. It's all open source. And in particular, there's a lot on the NASA Lambda website, which is this one. It's a toolbox that includes lots of different codes which are used for different parts of these analysis. So in particular, for Euclid, I'm in charge of the forecast analysis, so of trying to understand how well Euclid will perform with the data, let's say imaging the data that we will have in order to actually test gravity and fundamental physics. And for the science ground segment and for all the forecasting task force that I'm coordinating, we chose Python as the recommended language. Although, let's say, the point is that we have lots of different codes also written in different languages that have to be combined together. In particular, for the interpretation, so to get from the actual spectrum to understand what are the parameters of the model that actually better fit the data, we need to perform Monte Carlo simulation, Markov chains. So get a list of samples of the posterior distribution. Usually this is done in Bayesian statistics, in Bayesian analysis. And so it's really important to be able to sample the space of parameters in a very effective way, because typically you need to sample a space with many parameters. You have to test for models in which usually there is at least, let's say, of the order of 6-10 parameters that describe the energy and the evolution. But in addition, there's mainly about 100 parameters that describe all the systematics, all the foregrounds, all the things that you have to keep under control. And you have to do that many, many times for different data sets to understand how, if all the different data sets that we have coming from different experiments are compatible, if they're not compatible, how you can extract the most information from it. So there's different codes that do that, and we try to have challenges in which basically you have a blind analysis. You don't know what's the actual true universe, and you test different codes, just giving them some say fake data, and you try to see if they match and which is the one that best reconstructs the original cosmology. Now, one of the codes which is used for Monte Carlo simulations is called the Monte Python. It's written in Python and it's publicly available on the GitHub repository. There's documentation. The main developers are Benjamin Audren and Julien Lesgourge. They're also, actually he's now in Euclid. He has left Euclid, but he's still working also on its development and many, many others. So the extraction of cosmological parameters is complex. It uses different likelihoods from different data sets. There's several free parameters. So it's, again, as I was saying, very important to sample very efficiently parameter space to be able to run Markov chains for many, many different models, and to be able to actually implement those models to describe different sets of equations. So whenever there is a model, you need to say, first derive all the equations that describe how these tiny temperature perturbations evolved and changed from 13 billion years ago down to today. You have to solve them with several codes, and then you have to link that to a sampler that, again, does simulations changing the values of different parameters and tries to see which are the parameters of the model that best fit the data that you have. For a long time, and actually it's still one of the most used, that's wrong, sorry, that should be a C, not an S here. One of the most used codes for samplers for that is Cosmo MC, which is also publicly available, developed by Anthony Lewis now in Sussex. And more recently, there's Monte Python, which is the Python, say, competitor or equivalent. Python in this case is convenient because it's much more concise than the previous code. So it really, optimized a lot the code with respect to what we had before. You can run very stable Markov chains for several days. And the most important thing is that it has a moduled structure, because the main problem is that you have to interface several different codes which do different things. Some of them, like there's part of them that take care of the evolution of all the perturbations, all the temperature perturbations in time, and then there's part of them that does at the actual sampler, and there's part of, say, other modules that instead take care of different data sets. So they implement likelihoods for different experiments, and all of this has to be joined together, and possibly all these modules are typically developed by different people in different groups, in different parts of the world, and in different languages. So that's more or less the structure of all the modules which are in Monte Python. That's the main sampler. That's the part which is connected to the Boltzmann solver, so basically to the part that evolves the equations from the past until today. That's the part, the likelihood part, all on top. So there's a module for each experiment. There's for Planck, there's forecast modules, so to predict what the future experiments will be, or others to actually use the real data. And there's different samplers that have been tested and used to check, let's say, depending on what you want to do, some of them might be more or less efficient and also more or less developed. There was a tentative, let's say, I think it's also on Binder. So to extract IPython notebooks to have some interactive page for at least a part of this code. That's for the class part. Class is the part that actually evolves the equations. So it doesn't include the sampler yet. And there's basically Python wrappers which are used to connect this part to the actual sampler. At the moment, what is not yet optimal in Python is the fact that, well, first, it's really just relatively new with respect to the other ones. So it has been less tested, although we're working a lot for it at the moment in Euclid. There's lots of parts which are still a bit slow and computationally expensive. And yeah, it would be nice to have something equivalent to OpenMPI, which is unfortunately at the moment not available. So if you have ideas, of course, feel free to send suggestions also to the developers. We're actually also looking at the moment, I think, for IT students to optimize the code, which is now not completely compatible with Python 3. Apart from the sampler, Python is also used a lot for plotting, actually, and to extract information from all the Markov chains and get plots like that, so likelihood plots, in which here you have all the cosmology parameters, so all the parameters that describe how much dark matter, how much dark energy, how fast is the expansion of the universe, which were the initial conditions, and each ellipse, I don't know if you have ever seen that, but these are probability contours at 68% or 95%, 99%, to have your parameters in that region. So this tells you which parameters are compatible with the data and with which probability. So for that, the best tool that we have at the moment is all completely written in Python, and it's also available. It's getDist, part of the Cosmology package. It's also available online. That's compatible with also Python 3. And it mainly uses lots of implementations of the matplotlib library. So you can get, for example, plots like that, 3D plots, in which you combine different cosmological parameters. That's, for example, the expansion. That's the amount of dark matter. That's the amount of perturbations of structures, galaxies, let's say, that you have today. And each of the lines and contours and dots are basically referring to different data sets and different experiments. So when you do that, that is used to, for example, test whether new data are actually compatible with the theory of Einstein, with general relativity, or whether you actually need to modify general relativity, so to modify the theory of gravity, in order to explain this accelerated expansion. And at the moment, this is one of the biggest challenges. So to understand whether we really need an extra particle, an extra form of energy, which is, again, as I mentioned, called dark energy, or whether you really have to change the equations of gravity, so whether you have to change general relativity, and whether there's something that we don't understand about that might explain this acceleration. So that's part of the latest results that we got from the Planck collaboration. These are just, let's say, parameters. Let's say when they're 1, so here, this point corresponds to the standard model, Einstein, general relativity. But the fact is that the data have actually shown that when you combine the information from the early universe with information that comes from late time probes, most of the probability is actually here. So it's away, it's kind of, this is 3.5 sigma away from general relativity. So that's not, of course, 3.5 in cosmology is not a detection, but it's still attention, and it's still actually now really bothering lots of us because, well, actually, it's also the interesting part because with the future experiments, we hope to be able to restrict these ellipses more and more, so to have higher and higher resolution, and try to understand whether we really have to stick to general relativity, or maybe there's some change in the equations that might explain why we are in an accelerated universe and what is this dark energy. Ultimately, this is about our future and the future of the universe. So how the dark energy will evolve will decide whether we will all expand, let's say, forever, whether there will be, so if there is enough dark energy and if it starts, let's say, to dominate completely and expand faster and faster, everything will be destroyed into a big rip. So everything will, the density, let's say, of the galaxies will become lower and lower. Everything will be just wrapped apart. If instead it slows down and dark matter starts to dominate again, so matter and ordinary matter starts to dominate again, then this acceleration might stop. And actually also in this case, the future is not so promising because everything will just collapse again. And yeah, so I'm not sure actually if there is, I mean, at some point it's a matter of taste whether we will just collapse completely or expand and destroy ourselves in the opposite direction. Anyway, the next wanted thing is the imprint of gravitational waves on this radiation. So you might remember that last year there was a direct detection of gravitational waves from ground experiments. And the next challenge is to detect the effect of these gravitational waves on this radiation. This is a very, very, very difficult signal to detect. It's seen on the polarization, so not just the temperature, but really the directionality features of the light that comes from the early universe. And yeah, so at the moment, what you see in this sort of impressionist picture is actually what has already been detected by Planck. It's the polarization of the light, but it's not, unfortunately, the primordial light. So it's not the light that comes from the early universe. It's just the polarization from the dust of our Milky Way. So we actually want to get rid of that. That's bad. That's our background. Yeah. But for some, well, I mean, it's still a nice picture, so I guess I put it. Okay, so there's a revolution to come in the next 5 to 10 years, I would say. I think in the next 3-5 years, there's probably going to be at least detection of the dark matter part, the dark matter particle. But to unveil the dark universe, well, that's a big data challenge. There's been a lot of investment from all over the world, from ESA and NASA. Actually, Europe has a main role in this. And so it's important to get the best scientific return. And of course, since we have lots and lots of data and lots of challenges, again, in the signal processing and in the interpretation, this involves large convergence of different communities which are experts of different things and need to work together. And that's actually also one of the main challenges in these large collaborations. So that's it. Thanks.
Thank you. Are there any questions?
Hi, thank you for your speech. Very interesting. Can you tell us something about the scale of the data you're processing with the Python scripts, for instance?
The scale? What do you mean the scale?
Well, like the dimensions of the matrices you're loading into memory. Do you do some parallel processing?
It's terabytes of data, and usually, again, we have about at least 10 parameters which describe the cosmology. So, for example, the amount of dark energy, the amount of dark matter, the expansion of the universe, primordial initial conditions, okay, more or less, about 10 parameters. And then there's about 100 parameters in addition that describe the systematics. Systematics means how you can model the foregrounds, all the parts that you have to get rid of. And since there's lots of uncertainties there, you need to introduce parameters and try to marginalize, let's say, over a certain range of uncertainties for each of these parameters. So usually, at the end, you will have matrices of at least, let's say, 150 parameters square. And that's for every single model. And then you have to test that for a variety of models or for additional parameterizations, which include classes of models. And on top of that, you have to do it for different data sets. And you have to do them separately for each data set and combining different data sets in different ways so that you get control of what actually each data set is telling you. So every run, let's say, can take a week, let's say, depending on the complexity of the model. You can go from, okay, the standard model, let's say, paradoxically, it's standard also because it's easier to test. It has the least number of parameters, and it can run maybe in a couple of minutes, or maybe, yeah, okay, 10 minutes, half an hour. And that's actually the uncomfortable thing. So the fact that the standard parameters the standard model is also the one which is easier to test. And so that's why there's a lot of work now to try to implement better codes, faster code that can actually test a wider range of models.
Okay, there were some questions here. A lot of questions, actually.
Thank you very much. Really interesting talk. I can't think of anything more interesting than learning about the origin of the universe. Why is the background radiation not uniform?
Not uniform. Amazing question. Yeah. So that's a very good question. So the origin of this very, very tiny temperature perturbation is due to quantum gravity, which usually just means that nobody knows what it is. It's a very vague answer, but really in practice we don't really know the origin of these tiny, tiny perturbations. But if they weren't there originally, we would not be here now. Because actually, these tiny temperature perturbations were then the seed to the density perturbations that then formed all the galaxies and all of us afterwards. Yeah.
I think there's time for another question.
Thank you very much for this trip in space and time. I have a couple of questions. Can I? No, just one. Okay.
We can chat in the coffee break as well if there's more questions.
Okay. Maybe it's a stupid question, I don't know. But, do you have to cool down the receivers in the satellite?
That's a super important question. Absolutely, yes. So the detector is cooled at 0.1 Kelvin. It's, again, as I said, the coldest place in space. Let's say human place in space. And that's also why the experiment could only take data for 2 years, 3 years actually, because it needs a very sophisticated cryogenic system that could not be stable, let's say, for more than 3 years. And the reason is that you need the temperature to be really, really stable and very low in order to get these tiny, tiny, tiny differences of 1 part out of 10 to the 5th. So that was the main limitation of the satellite, of the Planck satellite. The other one, Euclid doesn't have this problem because it's mainly looking at a different source. It's looking at galaxies and shapes of galaxies, which are a recent thing. Let's say they are just a billion of years old. But the Planck satellite was really looking at this cosmic microwave background that was, and again, it's tiny, tiny difference in temperature, sourced 13 billion years ago. So really, that's the farthest we can look at in the past.
Thank you.
I would like to know, do you save data from every computing steps for different questions, maybe? I mean, you have to get rid of the rumors of our galaxy from the data, but maybe is it useful for something other studies?
Yeah, absolutely. So when I say it's foreground, I mean foreground for cosmologists. So it's things that, for example, we cosmologists want to get rid of, but there's other communities in astronomy which are actually interested in understanding the Milky Way, for example. And so there's a huge other community which uses our foregrounds for their own studies. And even, for example, the dust, that was used also to understand that other experiments who had claimed that they had seen the gravitational waves, for example, on the CMB. I don't know if you heard of the BICEP. That was an experiment that was in the South Pole. At some point, they claimed that they had seen the gravitational waves, and instead it turned out that it was dust, let's say, from the Milky Way. But again, that's still interesting. There's different consortia which then use different parts of the data. And all of that is saved, and that's another issue because there's a huge amount of data that we are collecting.
Thank you very much, Valeria.